Hello, and welcome to BME 295, Introduction to Electronics. This is going to be our LTSpice tutorial number 2, where we'll begin looking at time-dependent and frequency-dependent circuits and how we can analyze those in LTSpice. So if you haven't yet, please pull up your LTSpice program. And I would suggest that you follow along with this video, pausing where you need to in order to place components or figure out where things are. As I mentioned in the previous tutorial video, there are some Windows and Mac differences. I am running this on a Windows machine, but I will point out Mac differences where they occur. And everything that you can do on Mac, you can do on Windows. Unfortunately, everything you can do on Windows, you can't do on Mac. So it'll be a little bit more difficult for Mac users, but not too much more difficult. So last time we covered how to look at DC circuits and how to analyze DC circuits. To me, the far more powerful aspect of LTSpice is the ability to analyze signals that are in the AC domain, the alternating current, or arbitrary input signals, because these encompass a wider class of circuits and inputs that you'll be interested in as a biomedical engineer. So let's go ahead and get started. To start a new schematic, we again click File, New Schematic, or Control-N. You can also get to it if you're a Mac user by right-clicking, or the equivalent of right-clicking on a Mac, and going to New Schematic, which pulls up our schematic screen. So let's go ahead and design a low-pass filter, an RC low-pass filter. So we'll do that with a simple resistor and a simple capacitor. So we can place a resistor. If we wanted to rotate the resistor, we can hit Control-R, and that will rotate it. Again, right-clicking will get rid of the component, and we can go up to capacitor and grab our capacitor here. Now, if you're a Mac user, again, you'll have to go to right-click, and then go to Draft, and then Component, and then you'll have to find your resistor and your capacitor here and place them as such. All right. So for both Windows and Mac users, we'll have to get to our voltage source here underneath the component, which for Windows can be found on the Component tab. For Mac users, again, we can right-click, go to Draft, Component, and our voltage source. So something of note for the voltage sources in LTSpice is that they serve as a voltage source for both AC, DC, and arbitrary signals. So to get to that, we'll just right-click, and under Advanced, we will see functions that we can put into our voltage source, including pulses, sine waves, exponentials. I'm not entirely sure what SFFM is, probably a frequency modulation of some sort, a pulse width, and an arbitrary file here. For now, let's stick with our sine wave. And as soon as we click on a particular function, we'll notice a set of parameters come up here. These parameters will come into play for two of the analyses that we'll use. So DC offset just applies a constant voltage. You can think of it as another voltage source in series with the cosine source to sort of raise or lower the DC level. For now, we'll just set that to 0. Amplitude, for now, we'll just set to 1 volt. Again, this we can manipulate and play around with. Frequency becomes a little bit more interesting. So for now, let's set this at 500 hertz. T delay is the, so when we run a simulation, there's a start time. We can delay the turning on of the stimulus, like having a switch in the circuit, like we do in class. But for now, let's just set that to 0. We just want it to turn on right when the circuit starts. And a phase shift. So if we wanted to have this be a sinusoid, or a sine rather, sine function, we can just have this be a 0. If we wanted this to be a cosine, we put in 90 degrees here. Oh, my apologies. I confused the theta with the phi. The phi is our phase shift, so 0 for um, sinusoids and 90 degrees for a cosine. These other parameters are not important. We can leave them blank. We'll come back, but I want to point out the small signal AC analysis. We'll come back to that here in a second, but this will be important a little bit later. Now, everything that we do so far in this class deals with ideal voltage sources. We can also set parameters to deal with non-ideal voltage sources, or to model non-ideal voltage sources. For now, we won't need to worry about that. All right, so now you'll notice that a function has appeared below the voltage source. For Windows users, if you want to move this, you can click to drag. For Mac users, you again have to right-click and go to Edit and get to drag. For Mac users, it might be useful to sort of get used to some of the hotkeys that are associated with this. Might make things a little bit easier. And we'll just sort of organize our circuit so that we can see everything happening here. Okay, so a reminder for Windows users, we can go to wire up the circuit. Also, we can go to draw wire under draft for Mac users. So we'll just draw a wire here and connect the circuit up as so. Remember to double click on each one of the terminals to terminate the connection. All right. And a reminder, because this is effectively a node voltage solver, we'll always need to set a ground node. So let's set a ground node here at this common terminal. It has the most connections between the different components, so it will serve as a good ground and reference source. So we built our circuit, and now we're at the phase of where we left off last time, where we could do a DC operating point analysis to look at DC currents here, but we've got an AC current going through here. So how do we analyze this? Well, for Windows users, if we go to Simulate, Edit Simulation Command, we have this nice menu pop up for us, and we can do a transient analysis. The transient analysis allows us to look at the circuit at a single snapshot or a single frequency. In this case, the frequency of this sinusoidal function that we have set earlier. So we have a stop time, meaning that our circuit runs from 0 to stop time seconds. Because we're at 500 hertz, we don't need all that long to resolve the circuit. If you have slower or lower frequencies, so slower time forms, you might have to drive your stop time out further so that you can resolve the full signal. But for now, 500 milliseconds will be great. Time to start saving data. That's when we actually want to start recording things. Let's just record through the whole cycle. So we'll set that to 0. And maximum time step, we can let the program decide that for us by leaving it at 0. Or I guess at no inputs given. Now, for Mac users, you're going to have to do this using commands. So another way to do this is by using what's known as an LTSpice directive and inputting that directly into the directive. So let me show you how to do that here. So for Windows users, once you click OK, you can just place it on the schematic. For Mac users, you'll have to go to draft, spice directive, and then type in the command here. So this is when to start recording, how long we'll record for, and the one of the other parameters, which I'll show you here in a second. I have to remember it myself. T-start. So we start at 0. We print 0 here. We can just leave that as it is, as 0. And we want to go up to 500 milliseconds. Okay. So now we've got this going. So we can just right click and hit run. Oh, my apologies. I forgot to, and this will happen to you all the time. I forgot to declare my values. So let's go to our values here. Let's make this 1 kilo ohm. And let's make this 0.1 microfarads. So take a quick moment and pause this and do a quick calculation. What do you think the cutoff frequency for this is? Remember, anytime that we see a RC circuit like this, we should be thinking filter. So go through and calculate what the cutoff frequency might be in this circuit, and we'll verify that here in a moment. Okay, when you're ready, we can click run here, and hopefully, if I did everything correctly, the simulation should start. Now, kind of similar to the operating point, we have to specify which node we want to measure the voltage or current off of. In this case, we want to look at the voltage across the capacitor. So with our mouse, we'll just click here. And up on this screen, then we can see the output sinusoid. So something you should be noticing here is that we have a signal that is pretty darn close to what the maximum signal is here at 1 volt, meaning that we're probably pretty close to the passband, but maybe verging on getting to our cutoff frequency a bit too, since we have a little bit of a drop. If we can run again and then click another spot, let's say right here, and that will give you the input. And so we can start comparing sinusoids. So from input to output. Now, kind of as you would expect, we are seeing maybe an amplitude drop as well as a phase shift. In this case, the blue is our input and the green is our output. So we see a little bit of a like lowering of the absolute magnitude of the signal and it being shifted to the right in time. So that's kind of what we are expecting. Now, maybe the more powerful analysis is going to be one where we sweep frequencies throughout the circuit. So to do that, we'll right-click on our voltage source, and going back to the small signal AC analysis, we can then specify the same input amplitude and input phase, but what this is going to do is allow us to simulate a multiplicity of frequencies. So we can start sweeping frequencies and see how the circuit responds. To set up that analysis, again, we'll go to Windows users here. We can go to simulation. I have to click on the lower schematic first. We go to simulate, edit simulation command, and go over to AC analysis. For Mac users submitting a SPICE directive, this command is .ac with these parameters. So the first thing we need to set is a type of sweep. So if we click on that, we see that we can do an octave, a decade, a linear, and a list. So linear sweep just sweeps linearly through frequencies. What I find best for understanding how the circuit might behave with the least amount of computation is an octave. So the octave basically acts as our logarithmic sweep. So for the number of points per octave, we usually have to set somewhat high. It depends kind of how wide of a frequency range that we'll do, but you'll notice that these computations happen pretty quickly, so we can set this relatively high. Let's say 200. So we see down here for the SPICE directive, that's changed to .ac oct 200. So let's choose a start frequency of 0.5. That should be okay. And a stop frequency of 100K. And that will give us a pretty good idea of what the sweep looks like. So I hit OK. And you'll notice something here is that there's a semicolon in front of our previous SPICE directive, the semicolon tran. That is a comment in SPICE directives. Placing the AC here for Windows users then allows us to run this simulation while commenting out that. For Mac users, again, you can right-click on your old SPICE directive, and you can comment it in or out. You can also, I'm just going to write this as a comment, but if you're a Mac user, you'd hit period here instead of semicolon like I'm going to do. But you can just simply type in the same directive, and that will do the same thing for you. It will change it. I have it commented out, but it will change it for you so you can switch between analyses. So let's get rid of our plot here for the original one. And now let's run this through. Okay, so we have to choose a node to which we want to measure. So we'll do that here. All right, so the first thing I want you to notice is that we have two plots happening here. A solid line, which is going to be our amplitude response, so our magnitude response, and a dotted line, which is going to act as our phase response. So the .ac command gives us both magnitude versus frequency and phase versus frequency plots, which is quite useful to have. So the cutoff frequency is just eyeballing it roughly 1.5, 1.6 kilohertz, which if you did the math should be about correct in this simulation. We can also zoom in and look at different parts of the waveform as well, and right-clicking and hitting zoom to fit will bring us back to our original view. So now we start to get an idea of how filtering might work, or how a circuit might filter an individual signal. So let's look at something maybe a little bit more interesting. I'm going to close out of this, and I'm going to open up a new circuit, or a circuit that I had already made. In this case, this is the Warburg electrode-electrolyte interface model. You'll start to see this model more and more often, especially as you go into more bioelectronics. This is a model of a tissue-electrode interaction, where this voltage accounts for the half-cell voltage, which is a property of the electrode material, as well as two resistances and a capacitance. I've also added a load resistor here so that we can measure a node. What these are modeling are not important for this lecture, but we'll get more into it later. Just to say this is a more complex circuit than what we had previously done, but we can apply the same analyses to these that we did previously. So pause this video for a second and build this circuit on your own. Go back if you need a reminder on how to place components, or like how to get to individual components. But unpause whenever you are finished. Okay, so just a reminder for this voltage source here, we're going to set this to about 0.7 volts. This resistor here to 500 ohms, this capacitor to 1.5 microfarads, and this resistor to 50 ohms, and the load resistor to 100 ohms. For this input sinusoid, I had the parameters shown here, which you can see on the SPICE directive as well, but we just have an amplitude of 1 volt and a frequency of 1000 hertz. And for our small signal, we have an AC amplitude of 1 and a phase of 90. Actually, let me put a phase of 90 here into our transient analysis as well, so that we're consistent. So you can input these SPICE directives as you see fit. I'm going to say this was just sort of an approximation by my point. This wouldn't be a particularly good electrode, but you can sort of get the idea of how we can start measuring bioelectric interactions using LTSpice as well. Okay, so let's start off with a transient analysis here. So I'm just going to get this running by deleting the semicolon and putting the period in front of tran, and that will activate that. I have to go to the AC analysis here and make sure I comment this out as well. And now it's commented out. So now we're just passing a 1 kilohertz sine wave through the circuit. So if I hit click run here, and let's choose the voltage across this load here and the voltage here. Now we notice that our output has a bit of shift upwards. That's because of that 0.7 volts. But we can start seeing the individual waveforms across each as well. And this, while this is interesting, it's not particularly informative for this particular circuit. So let's go back to the actual AC analysis, which is much more informative. Oftentimes when you're trying to interface with the nervous system or any sort of tissue, you're really worried about how that electrode is going to connect to your tissue in terms of impedance and how that's going to affect your frequency response. So this is a little bit more of a valuable analysis. So let's run that. Again, actually, let me close out of this so that we can get a cleaner figure. And like I said, what we notice here, this time we're plotting the amplitude response here with the dotted line and the phase response here. You can set up a menu as well. You can mark data points, visible traces, and other things as well. So we can say, or choose any one of the nodes, the voltage or current. Oops, and choose that. I chose a poor one, unfortunately. If that happens, we can just click out here, run again, and take a look. So we have magnitude here in the dotted line and phase here in the solid line. And we see that this is acting as much more of a bandpass-like effect, which may be desirable on your electrode, probably is not this narrow of a bandpass frequency. So we know that electrodes with these properties might not be particularly good at recording bioelectric events, depending upon what bioelectric event you're looking at. If you're trying to record from neurons, this would not be great. Might be okay if you're looking at something like an EEG. But that will about end this tutorial with LTSpice. Again, the AC command and as well as the transient command allow us to visualize time-varying signals in interesting and important ways, and allow us to analyze frequency responses, which becomes very important when we're looking at filtering, especially as we're designing interfaces so that we can interface with biology. Thank you very much for tuning in. As always, if you have any questions, please don't hesitate to email me, and I'll answer them as they come in. I hope you have a wonderful day.